The first presenter for today is Alan Żmuda. He is from a Faculty of Physics, Astronomy, and Applied Computer Sciences of Jagiellonian University in Krakow, and he will give us a talk about the chemical evolution of phosphorus and its influence on the origin of life. I will let you know after 10 minutes of your talk that you have 5 minutes left, and the space is yours. I can't hear you. I'll check these. All right, take your time.
Right now?
I can hear you now. All good.
Okay, lovely. Yeah, I was just checking my battery if it's gonna work. But
hopefully not. You have half of it.
Okay, so maybe let's start. Many people over the centuries have wondered about the origin of life on Earth. Some believe that it arose due to interference of an unknown divine force. Others speak of the extraterrestrial origin of life, and still consider its creation to be a coincidence. At the moment, we know what condition must be maintained for life to arise and develop. At least that is true. It's about life that we know. However, before we get to the question of the formation of life, it's necessary to go back to the concept of what life is made of, how the atoms necessary to start life is necessary to go back to the concept of how the atoms necessary to start life were formed, with the main emphasis of the formation of phosphorus in the universe. At first, I wanted to start with the question, why phosphorus? It is worth considering what role it plays in the functioning of living beings on our planet. This element is a component of nucleic acid, the universal energy carrier, which is ATP, and hydrogen transporter, which is NAD. The amount of this element in organism is not high, but its role is very important. For example, phosphorus deficiency causes a limitation in the synthesis of ATP, and this compound is necessary for important energy transformation in cell. Provides bonds elements with hardness and strength. It takes part in cell growth and regeneration processes. Participate also in the metabolism of fat and starch. In plants, its deficiency causes a reduction of photosynthesis and disturbance of cellular respiration. It is a factor limiting the growth and development of above-ground parts of plant and droughts. A major open question in evolutionary biochemistry concerns both the role of the phosphorus compounds in chemical evolution that preceded the emergence of life on Earth, and the main source of such phosphorus compounds are two main topics that I want to talk about today. The main idea behind the first concept is are the two theories of the origin of life on Earth. This is a theory of primordial soup and RNA world. These are actually relatively related theories about the possibility of synthesizing simple or organic compounds in a spontaneous way using high energy and under appropriate environmental conditions. it has been shown that even slightly more complex compounds, such as oligonucleosides, can be formed in this way. The discovery of the acids in the Martian meteorites, the detection of PO2 and PO3 anions in the mass spectra of fully interstellar dust particles, and the high content of phosphorus and carbon in these particles. Based on this above three observations, we suggest the possibility that meteorites and comets deliver relevant molecules to the early Earth through extending the role these bodies played in creating biochemical compounds on the primordial Earth. To this end, we will consider the role of phosphorus in chemical evolution for interdisciplinary point of view, giving a brief overview of the main stages of this element from the formation in the course of stars through its processing in interstellar space and in various cosmic bodies. The later supposedly interacted with our planet. Then we discuss the relevant data available, and finally conclude with some suggestions that may be of interest to gain deeper insight into the importance of the biogenic element for the observations and experimentally point of view. Starting with the hydrogen nucleid formed during primordial nucleosynthesis that took place shortly after the Big Bang, stars have been producing helium for most of their lives. The highly stable nuclide becomes the basic building block of subsequent nuclear reactions, which, starting with the triple alpha process, first produced the important element carbon, and then from successive alpha captures gave rise to oxygen and neon. Oxygen in turn is a basis for the synthesis of sulfur. Therefore, after reading stable, the question about the origin of phosphorus nucleid arises quite naturally. Considering the key biogenic elements in turn, we have carbon, which is the 15th most abundant element in the Earth crust. It has a unique ability to form polymers and various organic compounds. Oxygen is the most abundant element on Earth. It is the third most abundant element in the universe. Many of the major classes of organic molecules in living organisms contains oxygen atoms. Nitrogen, the human body contains about like 3% by mass of nitrogen, the fourth most abundant element in the body after oxygen, carbon, and hydrogen. And sulfur, which is the 10th most massive element in the universe and the 5th most massive on Earth. Sulfur is also essential element for our life, but let's skip to phosphorus nucleosynthesis. Before we move to that, a few words about the element. The phosphorus has concentration in the Earth crust of about 1 gram per kilogram. It is an element necessary to sustain life, mainly through phosphates, compounds containing a phosphate ion. Phosphates, on the other hand, are components of DNA, RNA, and ATP, and also phospholipids, complex basis compounds for cells. An important aspect is the fact that the element of phosphorus exists in two main forms, white phosphorus and the red phosphorus. But because it's highly reactive, phosphorus is never found on Earth as a free element. In the absence of significant mass loss, massive stars with masses between 15 to 100 times bigger than the mass of the Sun carry out a natural sequence of nuclear reactions. These reactions continue with interruption until a sort of onion structure is built around the core formed by the peak elements of iron, according to the sequence which would start with hydrogen, helium, carbon, oxygen, nitrogen, magnesium, silicon, and iron. This is not.
You have 5 minutes left.
Okay. This reactions. This is not the case of less massive stars, because significant crossroads in stellar evolution occur when the so-called starburst beings call combustion process, while the most massive stars enter this combustion phase peacefully. Immediate mass stars from 4 to 8 solar masses can be completely torn apart by carbon ignition. The stars slightly less massive than these will burn no carbon at all and will likely become white dwarfs after losing enough mass during these phases. Okay, so let's start with nucleosynthesis. After the consumption of carbon and before the ingestion of the oxygen, there is an episode when a neon is broken down by photodisintegration. The resulting alpha particles are consumed by the present nucleics in a process called neon combustion. This is where we see this reaction. This scenario takes place in the inner zone of massive stars, undergoing hydrostatic combustion of the carbon, followed by explosive combustion of neon at 2.5 billion degrees of Kelvin. It is under this condition that we find the original origin of most of the natural nucleids when we're talking about phosphorus. Let's skip to mass distribution of phosphorus in the Earth crust. There are certain environments on Earth that are rich in chemical elements such as carbon, oxygen, iron, and phosphorus. There are 3 specific aggregates of phosphorus on Earth. It's ingenious metamorphic rocks, lands, marine sedimentary rocks, and oceans. While it is estimated that the total amount of phosphorus in the environment consists mainly of ingenious rocks and marine sedimentary rocks, total mass which is 8.2 multiply by 10 power to 20. It's estimated that approximately a 6.3 are trapped in the biosphere alone. This estimated as calculated, assuming that the total mass of carbon in living organisms is 10 power to 18 grams. Assuming as average ratio of phosphorus to carbon, we get this number if instead of total amount of phosphorus, we take its circulation in the oceans. There it's relatively low. Although we know a little about the conditions on the primordial Earth, the above capture scenario of, I don't know if I have enough time. I think I...
it's okay. You have 1 minute, but you can sacrifice the time for discussion.
Okay. So maybe I will skip the phosphorylation because it's actually the clue of my presentation. The phosphorylation in the endogenic reactions involving the addition of phosphatate mainly form on inorganic phosphate biochemistry, has shown us that the wonderful function of phosphatase, like energy transduction, replication, etc., in living organisms, function that difficult for the inorganic compounds such as arsenics or silicontes, etc. On the first successful experiment on the phosphorylation of probiotics at relatively low temperature, which is 35 degrees of Celsius, was conducted by Miller and Paris. They demonstrated that the pyrophosphates formation in 27% yield from hydroxyapatite and potassium cyanide. Okay, I think I'm running out of time right now.
Yeah, I mean, if you want to go to discussion, we can, but you have how many minutes? 4 minutes until we have to go to another speaker.
Okay, I think I will need this 4 minutes to take a bigger view on this point.
Right.
Okay, so the synthesis of polyphosphates was obtained in a similar way. The authors consider these reactions to be plausible probiotic models. I would like to suggest that above reactions are good candidates for a localized probiological phosphorylation, and the precursor of phosphatate, ammonia or ammonium salts for these reactions were obtained in the late accretion period. As mentioned earlier, comets can be suitable source of ammonia and phosphate. My suggestion is based on the following facts. Ammonia is known to be present in comets. Phosphates have been detected not only in chondrite meteorites, but also in interplanetary dust particles of cometary origin. Mass spectra of probably cometary origin showed masses corresponding to PO2 and PO3 ions. But actually, we still don't know how this is possible, that the life that we know has been created. To summarize, comparing the nucleosynthesis of the main biogenic elements like carbon, oxygen, nitrogen, sulfur, and phosphorate, where we realize that the case of phosphorus is unusual. First nucleate, which is 31 phosphorus, it's never mind. Nucleosynthesis can only take place in a smaller subset of stars that are massive enough to ignite carbon and nitrogen fuels. The Earth's crust contains ingenious metamorphic and sedimentary reserves of phosphorus, the amount of which is currently approximately 8.10 to 8.3 multiplied by 10 power to 20 grams. We've calculated that during the late accretion phase, comets and meteorites intercepted by the primordial elf may have contributed more than 10% of this amount. And also this line through thought is reinforced by the fact that the late accretion process, in addition to phosphate, contributed to the formation of water, ammonia, methane, and many others organic and inorganic compounds that likely favored to synthesis of biochemical molecules. The process of probiotic phosphorylation and polynucleate synthesis probably occurred to the surface of phosphate minerals and clays respectively. They probably occurred in a local
Sorry,
environment.
Alan. Oh, we really need to move to another speaker, but
Okay.
I will invite you for a seminar at Polish Astrobiology Society, so you will have the full hour to talk about it. It's really a fascinating subject, and yeah. Well, unfortunately, I have to kick you out right now. Don't get offended.
Okay, don't worry. Yeah, it's fine. It's totally fine.
Yeah, thanks for your talk.